Thank you everyone for coming. This program. Here's a Zach Kraus, a meteorologist from the website swctweather.com. Thanks for doing it, Zach. Go for it. Thanks.
Thanks for having us, Paul, and Larchmont Library, and thanks for coming, everybody. We know it's a beautiful summer day, and we appreciate you being here and spending a little bit of your afternoon with us. So I'm going to start quickly before passing it over to Jack. Paul, if it seems like I'm doing something wrong, if you can't see my screen, let me know. So today's presentation is going to look at the meteorology industry, and we're going to start with a crash course on weather forecasting from Jack, and then I'm going to take over and talk about some industry applications, and then we'll finish with questions. We're estimating it'll be about like 30 to 45 minutes, so not too long. Nice crash course. Before I pass it over to Jack, I'll just tell you who we are. So I'm Zach, and that's Jack. My name's Zach Kraus, and I am the Chief Meteorologist and owner of SWCT NY Weather, which is a hyperlocal weather forecasting service. We'll talk a bit more about what we do later, but we're located in the Southern Hudson Valley, and our third team member, Jacob, isn't here today, but Jack is, and we're happy to have him, and I'm going to pass the torch to him now as he takes you through a crash course on weather forecasting.
Thanks so much, Zach. Let's see if I can remember how to share the screen so you all can see this. Is this working, Zach? Well, I hope it's working. Anyway, so yeah, my name is Jack Sillin. I'm a forecaster for SWCT New York Weather, and I'm also a meteorology student at Cornell University. And I've been forecasting for my home region of Maine and New Hampshire for the better part of a decade, which is weird because not that old yet. So anyways, this presentation is meant to acquaint you with the basic principles of forecasting the weather. It can actually be generalized. A lot of these key themes can be generalized to forecasting of non-meteorological phenomena, and that's where we're going to start. Because it's important to understand prediction as a sort of framework for thinking about how we're going to talk about forecasting the weather, right? So before we talk about how to forecast the weather, the goal being to predict the future state of the atmosphere or some feature within the atmosphere, like this strong hurricane. This is Hurricane Dorian. If we want to predict this hurricane, which of course is of great importance to a large number of people, we're going to follow a process that is perhaps more easily understood in a simpler example, right? A hurricane is an extremely complicated phenomenon. Predicting it is extremely challenging. So to understand how we're going to approach that challenge, let's start first with something a little bit more simple. So suppose we have this train and we want to make a prediction about where it's going to be at some future state, or at some future point in time, rather. Well, what information do we need to know? Well, we need to know where the train is now. That's its initial position. We need to know in which direction it's traveling and how fast. And then we need to know how long our prediction interval is going to be. So this is a mathematical way of summarizing this. If the numbers and letters look complicated, don't worry about it too much. But basically, by taking these three parameters, is what we call them, four if you count the fact that the train might speed up or slow down over the course of time that you're trying to predict its motion. We basically, we can use these parameters to understand where the train will be at some future point in time. And we're going to adapt these parameters for a more complicated scenario in a few minutes when we talk more about the atmosphere. But a little bit more complicated of a scenario to continue with our theme of transportation here is what if we wanted to predict the future state of this interchange, where all the cars would be? Well, we need to know where they all are, where they're all moving, if they're speeding up or slowing down, how long how long they're going to be in this intersection, We might even need to know some information about where they're trying to go, because that'll determine which on-ramp or off-ramp they're going to take. But the moral of the story here, without getting too deep into the weeds of how you would go about making this traffic prediction, is that we now have a lot more variables in play, basically, to figure out where a train is going on a reasonably one-dimensional plane, right? You know, it's just some tracks, and it's not going to deviate from those tracks. Well, now that we're moving into a more complicated situation, our system of equations gets more complicated. But again, if you don't appreciate the algebra, then just appreciate the fact that we need to have information about. We need to have a lot more information to accurately predict the future state of this system than is capable of happening, right? We can't go around and ask every person where they're trying to go, for example, right? And if we don't do that, then we don't know exactly what this interchange is going to look like 5 minutes after this picture, or 10 minutes, or so on and so forth. So is this a lost cause? Well, thankfully it's not. We can still extract some useful information about the predicting the future state of this interchange, even if we don't ask everyone where they're going and how fast they're going and if they're going to speed up or slow down and so on and so forth. We can make some approximations and say, well, the people going on the on these straightaway passages here on the bottom, they're probably going to be going faster. People on the on-ramps and off-ramps, they're curving, so they're going to be traveling a little bit more slowly. So we can make some assumptions along those lines. And basically those assumptions are the source, or one of the sources of error in predictions that are complicated. Weather prediction, of course, being among the most complicated predictions that people in the world are attempting to make. Again, you can generalize this to predictions about the COVID epidemic. You could generalize this to predictions about the future state of the economy at some point in time. As soon as you start talking about these complicated systems, each one of these parameters that we talked about at the beginning, what does that system look like at the moment? That's not a question that can be answered completely in the case of the atmosphere or the coronavirus or the economy, right? No one knows perfectly what's happening even right now. And no one knows perfectly how that thing is going to change in the future. It's really a miracle, if you think about it, that we're able to give you weather predictions that are as accurate as they actually are today. Because as we'll discover in the next few minutes, there are huge errors that pop up in our predictions of the atmosphere specifically, that threaten at basically every stage of the process to derail our predictions. And the fact that we're able to hold these forces at bay pretty much, at least for the 7 to 10 day period, is a testament to how far the science has come in the past 50 years. It's pretty amazing to note that our 7-day forecast today is about as accurate as a 2 to 3 day forecast from the 1980s. That is true for both your local temperature, high and low, your precipitation, your snow forecast. It's also true for more consequential forecasts like the path of tropical cyclones and hurricanes. We're living in a remarkably predictable world, honestly, if you think about it, given how complicated these things are. Even though that might sound weird, because of course there are lots of predictions we fail to make. But if you recall from perhaps the 1970s or 80s, the numerous cases, not that I personally recall them, but I've read much about them, where your local weatherman said, all right, partly cloudy tomorrow, and you woke up with 8 inches of snow in your driveway, right? 8 inches of partly cloudy just does not happen anymore. And it will not happen again. Basically, as long as we retain our current knowledge of how the atmosphere works, we might tell you that you're going to get 4 inches of snow and you end up with 6 inches of snow. But those errors even are dropping off pretty dramatically too. So, all right, how are we going to go about making these predictions? Well, step one is to build a virtual atmosphere, right? We can't, mess with the atmosphere, at least on the time scale of weather. So we're not going to change where these things are going. But we can create a virtual copy of the atmosphere that we're going to play around with in a sort of virtual sandbox. Then what we want to do is make our virtual atmosphere look like the actual atmosphere, so that we're closely approximating, to the extent that we can, the initial state of the atmosphere. This is basically us trying to figure out where the train is right now. And when it comes to the atmosphere, that is a highly non-trivial question. What exactly is happening in the atmosphere right now is something that we don't really know on a sort of specific level. We know on a general level where it's hot, where it's cold, where there's a lot of moisture, where there's less moisture. But even if you think about some disturbances to the atmosphere think about the wind on some day. If you stood downwind of a building, right, and you notice that the wind is gustier than if you're standing in a field, well, that is an example of I can tell you as a meteorologist that there's some wind passing through your town, right? But I have no idea about all those gusts downwind of your building. You never know what those surprise gusts downwind of the building could turn into later on, as far as impacts to our weather forecast would go. So step 3, we're going to apply our governing equations. That's a fancy term for we need to know how the atmosphere is going to change over time. And there are equations that will tell us to a good degree of accuracy how the atmosphere will change over time. So this is the blueprint for how we generate beautiful simulations like this, which show realistic depictions of various atmospheric phenomena, including hurricanes you see down here. These would be called typhoons near the Philippines, and then these low pressure systems moving through the North Atlantic. This is a simulated loop here from one of our forecast models, but it produces a guesstimate of what the weather is going to be like, or what the atmosphere is going to look like, to a pretty high degree of accuracy. So that's pretty cool. All right, step 1 is building our virtual atmosphere. This is actually very easy to do if you have a little bit of knowledge of the Earth and computers. I know people who could spin up a simulation of the Earth's atmosphere in under an hour. I don't quite have the technological coding skills to do that yet, but hopefully I will be able to do that relatively soon. But if you want to do this to a high degree of accuracy, you'd use a giant supercomputer in the basement of some nondescript government building in Maryland or wherever they are. And then you tell your computer program some basic facts about the Earth. It needs to know how big the Earth is, how much mass the Earth has, where there's water, where there's not water, where there's forest, where there's grass. And again, even in this part of the process, there's room for error, right? Because I can't tell the model where every tree is, right? That's too much data. It's also data that's practically impossible to collect, right? To keep a running log of every tree on planet Earth. I mean, come on, that's way too difficult in a number of ways. So I'm going to make an educated guess about the approximate number of trees on Earth and where they're located. But that means that my model is going to miss some trees, and it's going to put some trees where there shouldn't be any trees. And even that will introduce errors into our forecast process. But anyways, we make our best guess, tell our computer what the Earth looks like, and move along. So step 2 is we need to find the right initial conditions for the current state of the Earth's atmosphere. And this involves taking a lot of measurements. So this on the right here is an image of all the weather stations, or most of the weather stations, taking observations every hour in the United States, in parts of Canada and Mexico. You can see that there are a lot of observations, right? But there are also holes, lots of rather large holes. So if I asked you what the temperature was over the central Gulf of Mexico, I could tell you, well, it's 78 degrees here northwest of the Yucatan Peninsula, and it's 66 degrees east of Brownsville, Texas. If I wanted to know the point, what the temperature is at the point in between, well, I don't know. It's somewhere between 66 and 78, right? Probably would be a pretty good guess. But we have to make guesses. And anytime you make a guess, you're going to be wrong to some extent, right? Even if I guessed 70 and it happened to be 70.2, that's still an error. And that error is going to turn out to grow rapidly in the future. So anyways, we have plenty of observations. That's great at the surface, but there are plenty of holes as well. On the left here, we have the points on the Earth's surface from which weather balloons are launched every day, twice a day. And because, of course, we don't just need to know what's happening at the surface of the Earth, right, which is the very bottom of the Earth's atmosphere. We would also like to have some idea of what's happening above our heads, because that's where most of the action happens. So to do that, we release weather balloons. This process is rather expensive. They cost tens of thousands of dollars each, and we release these twice a day at 978 stations across the world. So if you do that math, you'll very quickly realize why there aren't more of these dots. But you'll notice again that, well, we have pretty good observations here over the US, parts of Europe, parts of Asia are doing pretty well too. We have these huge swaths where we just have absolutely no idea what's happening higher up in the Earth's atmosphere. We can make some guesses using satellite imagery, but we have no direct observations above the surface across the vast majority of Earth, and not just in space, but also in time. If we were to zoom in towards our region, the upper air stations near New York in southwestern Connecticut, there's a balloon launch from Albany every day. There's a balloon launch from Central Long Island every day. There's a balloon launch from from Chatham, Massachusetts every day. So those are the three closest that we get. If you're familiar with watching the weather around this area, you'll know that that can cause some serious problems because the weather in southern New York, southwest Connecticut, can often be drastically different from what's happening on Long Island or in Albany. Consider the case of a winter storm, for example. It's very possible to have it raining in Long Island, pouring snow, dumping snow here in our region, and not snowing at all in Albany. So what are we telling our weather models in that situation? Well, we're telling them that there's rain in Albany, there's nothing happening in Albany, there's rain in Long Island, but those weather models have absolutely no idea what's happening over our heads. So that's a problem. Again, like these surface observations, we make plenty of educated guesses, but those go wrong with some regularity. All right, so our tool in our toolkit here, satellite data. These are points that are basically you can think of them more or less as equivalent to these surface observation points, but they're derived from satellites. You can see that this offers a substantial improvement over these observations here because we have a pretty good idea of what's happening over the oceans. Even over land, we have a denser mesh here of observations, but even here, there are plenty of holes. So anyways, the upshot of all of that is that we do not know what the atmosphere is doing right now, yet we still attempt to figure out what it's going to do in the future. And how we do that is we tell our fancy computers to solve all of these equations and many, many more that are much more complicated. If that makes your head spin, then that's okay. The upshot of this is basically that we take our incomplete understanding of what the atmosphere is doing right now, then we plug that information into these hugely complicated equations that spit out a picture of what the atmosphere might be doing in the future. And any error that you make in the initial conditions is going to be magnified exponentially as you move out in time. That falls out of how these equations are set up, basically. But you can think about that as every time, if you look over here in the zonal wind equation, you'll see this U squared thing. doesn't matter what U is, but if you imagine squaring something over and over and over again, right? Suppose that you're supposed to be squaring 2 over and over and over again. You get 2 squared is 4, 4 squared is 16, 16 squared is, I don't know, 256 or something. But imagine that you are actually supposed to be squaring 1.6 or 1.7 or 1.8. Even if you make that slight difference and you run that calculation out, you'll end up several dozen numbers off of where you should be. So that's a problem, and it's making our job here even harder. So as you can see in this little animation, we start out right here with a pretty good understanding of what the atmosphere is doing right now. All of these lines of the appropriate or of the same color are spaced relatively close together. But then as you move out through time, those tiny differences end up becoming larger and larger and larger until it's absolute nonsense and we have no idea what's going on. So this is why we can't forecast past 10 days. There's a limit basically that says, or there's a theory that says that we're never ever going to be able to predict past 14 days the specific conditions of the weather due to this chaos that emerges. Whether or not that's true, well, that's a subject of some very interesting debate, but that's basically what we're looking at the moment. So I'm going to finish up here with a quick tour of the weather models that we have available to us, the weather and climate models. And this is to give you a sense for some of the trade-offs made in weather models. It's also, you know, if you hear in our discussions or in discussions on the local news or wherever, you know, the GFS versus the European model versus the HER model, some of those terms are now making their way from the sort of ivory tower of meteorology into more popular culture. So hopefully you'll have a better sense of what those are and how they're different. So the main takeaway here is that different models have different purposes. So the climate models are these RCP, you know, in some number, 4.5, 6.5, 8.5, whatever. These are designed to predict the future state of the Earth's atmosphere in the time scale of 5 to 100 years. That's what they're for. They do not care where the thunderstorms are happening today. They do not care how much snow you're getting tomorrow. They are only interested in the general properties of how warm or cool or how much moisture there is in the atmosphere 100 years from now. This is why, you know, I often hear people say, perhaps you've also heard people say, well, if we can't predict what the weather's going to be 2 weeks from now, how on earth are we going to figure out what the climate's supposed to be like 100 years from now? Well, the answer is that to predict if it's going to rain tomorrow, I have to have a much more accurate picture of what's happening right now than if I want to tell you if it's going to be generally warmer or generally colder 100 years from now. So thankfully, by smoothing out those sort of day-to-day variability of weather, we can get a fairly accurate picture of what the climate's going to be like in the future. Moving down the timescales from that, we have these seasonal models. This is supposed to tell you, is it going to be a warmer or colder than average winter? 3 to 12 months is about where these models are looking. The models that you probably most often hear about and that we most often use are these synoptic weather models. These are basically designed to say, well, you know, is it going to rain 6 days from now? They're really working in the 2 to 10 day time range, although by 10 days they get to be fairly unreliable. And then we move even farther down to these mesoscale models, which are attempting now to figure out exactly where thunderstorms will pop up, exactly what time the rain is going to arrive, exactly how much is going to fall, so on and so forth. So all this may beg the question, do we even need human forecasters? We have all these models. They're remarkably good. They have errors that pop up after 10 days, but how much are the humans really going to be able to fix that? The answer is, well, at least past 10 days, not very much. But yes, we do need human forecasters. I don't just say that because I want to have a job after I graduate. But these two maps here, these are 3-day forecasts. This was from back last fall. These are our two main models, the European models on the top, the GFS, the American model on the bottom. 3-day forecast valid at the same time for a storm that was going to impact parts of northern New England. You'll notice that the ECMWF model's 3-day forecast calls for heavy snow extending from Maine down through northern New Hampshire, Vermont, into parts of eastern New York. GFS model at the same time is forecasting partly to mostly cloudy skies and not even a flurry. So if you're in charge of the Maine Department of Transportation, you need to know, are you staging your plows? Are you filling the trucks with salt? Are you calling your guys in from home to work overnight shifts here to make sure everyone can get to work in the morning? Models are going to give you conflicting answers to that, and that's where a human comes in and says, all right, well, I know from my training that the American model, this GFS model, tends to, most of the time, bring these nor'easters, these storms off the coast. It takes them too far east. So with that in mind, I'm going to hedge my bets towards the ECMWF, and I'm going to say, look, I think that there's a good chance that you're going to have to call in some of the plows, probably not going to be a major storm. Here's the timing. There's some chance that it could be a little bit more. There is some chance that the storm just doesn't show up at all, but that is a relatively minor chance. So, here are the actions that you should take to respond appropriately. So figuring out what those biases are, how to correct for the model's mistakes that we've talked about, that's the job of a human meteorologist. That's what we do at SWCT Weather. When we talk to folks at the libraries, when we talk to folks, local businesses, school districts, so on and so forth, people need to make decisions about how their various parts of their lives and other people's lives are going to be impacted by the weather. And to do that, you need to have information that's a little bit more complete than just looking at the models and saying, well, one model says snow, the other model says no snow. What's going to happen? Who knows? So that's where we come in. Hopefully that you've been able to follow along here and gain some appreciation for just how hard it is to predict the weather, and just how amazing it is that we're able to do as good of a job as we are, though there's still plenty of room for improvement. So with that, I'll turn it back over to Zach to talk a bit more about the meteorology industry.
Thanks so much, Jack. That was awesome. I love that presentation every time you give it. And I'm sure people have a lot of questions. Jack, do you want to mute yourself for the recording?
Yeah, I got to figure out how to get the Zoom window back. I'm so bad at these.
I did it for you. Don't worry about it.
Oh, awesome.
I'm sure you guys have a lot of questions for Jack about that presentation, because as awesome job as he does, it's still confusing, and we're going to take all the questions at the end. So what I'm going to talk about now is we now know how to forecast the weather. What can we do with this? So there's the obvious career paths that many of you know of, such as going to work for the government and being a weather forecaster, and being on air. Hold on one second, our phone is ringing and it's distracting me. I need to stop it. Sorry about that. It was going to bug me the whole time. So what can we do with our knowledge of the atmosphere now, aside from helping people to figure out if they can have their 4th of July barbecue tomorrow, or if we need to call in the plows like Jack was talking about? And there's a wide variety of industry applications, some very niche that I didn't know about, Jack didn't know about, until we really started to get more into our studies. And I think it's not evident to a lot of people. So the traditional career path, obviously, is on TV weather forecasting. When people hear the word meteorologist, they think the weatherman. And this is still existent, but a declining field. I'm going to show this like little video, partially because it's funny and partially because it conveys a point that I want to make after.
We had beautiful weather here for this weekend, mostly sunny skies and highs in the upper 80s. Overnight tonight, partly cloudy, mild, with those temperatures dropping down into the mid 70s. Now we've got some big changes here for the upcoming work week. Starting tomorrow, we're going to have a volcanic eruption right near Charlottesville, and it's going to make things rather toasty across the area. We're going to see lava spill out into central Virginia and make temperatures in Richmond at 350 degrees, Fredericksburg at 345, Charlottesville, the hotspot, at 400. Not as hot off towards the Tidewater. A little bit more comfortable with highs near 100 degrees. The reason why, we're going to have tidal waves moving in. Ahead of this, a global superstorm developing off towards the Atlantic Ocean. This thing is headed our way, but the key to the forecast, right before this thing makes landfall, it is going to be deflected by Godzilla. Now, a lot can change between now and then. We're looking at the latest data. We'll continue to bring you the very latest. I do want to encourage you, though, that if you ever do see a sleeping coyote, do not wake it. Bad idea. Okay, here's the forecast. Volcano 350 there for Monday. Global superstorm on Tuesday. We could see maybe about 200 inches of rainfall, wind gusts up to 1,000 miles an hour. Godzilla Wednesday, I'll be honest, I have no idea what's going to happen on that day. After that, though, how about this to finish off the work week? Low humidity, lots of sunshine, with highs in the upper 80s heading into next weekend.
Okay, so that is a April Fool's forecast. Hold on, I need to figure out how to get this. That is an April Fool's Day forecast that an on-air meteorologist gave. And part of the reason why I show that is because it's funny, but the other reason is because those kind of antics are becoming increasingly important in the industry, because people have shortened attention spans and people have other ways to get their weather data now much more quickly. If you ask people in my generation, even people who are really into weather, a lot of us are going to our smartphones or to weather.com for our quick forecast update and not waiting for the 6, 7, 11 o'clock news. So they need to figure out ways to make people want to watch TV for the news, whether it's putting on antics like that on April Fools, or making crazy graphics and using like augmented reality and all these crazy things. So that's where all these other career paths come in. As the traditional path of being an on-air meteorologist declines as people start to use more technology, we look towards these other career paths. The first thing to look at is the term public sector or private sector. So a public sector meteorologist is someone who goes to work for the government, whether it's a forecaster at the National Weather Service office. So as Jack was saying, our closest National Weather Service office is down in central Long Island. And those people, their goal, you could work for NOAA or NASA as well. Their goal is to promote public safety and like general knowledge in the industry of atmospheric science. So their main goal is to keep people safe, versus the private sector, which are private companies that employ meteorologists, and their goal, although is still to keep people safe, they're for-profit companies and usually have some kind of niche application that allows them to make money from their weather forecasting. So for example, we're a private weather forecasting company, and what we do is we provide hyper-local weather forecast for people in Westchester County, Putnam County, Fairfield County, and New Haven County. As Jack was saying, Long Island could be receiving pouring rain, Albany could be receiving nothing, and we need to figure out what's happening in White Plains, what's happening in Danbury, what's happening in Yorktown, New York, because people in each of those towns need to make decisions based on their town's weather forecasts. So we have clients such as the Larchmont Library and other libraries throughout the region and school districts, and we help them by giving them specific forecasts for their town and decision support in times of inclement weather. But there are tons of other private weather applications, such as this company, which is also located in the Hudson Valley. They're called Fleet Weather, and they do global cargo ship, global ocean weather forecasting, marine weather forecasting, and cargo ship routing. So that's another example. They help cargo ships figure out safe ways around storms, but also how they could more economically travel by taking advantage of like winds and whatnot. In a similar sense, airlines, every major airline employs their own team of meteorologists, and they even try to brag about why their meteorologists are better than some others. I was on a plane and I saw like in their security video footage, they put like a shot of their weather center in Delta's headquarters and like the superior technology that their meteorologists have and the things they're trying to add to their aircrafts to make them receive better weather data. So airlines are a big employer as well. And then we have cruise lines and things along in that sense. Now let's pivot. So that was like a transportation application. But now let's look at finance. So why would a financial firm employ a meteorologist? That's a good question. It is because almost everything we buy, its price is somewhat impacted by the weather. In a lot of sense, it's specifically the in a lot of senses, it's specifically the energy industry, but commodities and other things as well. So this is an example here on the bottom, Bespoke Weather Services. I interned there when I was in college, and they use those seasonal weather models that Jack was talking about and some proprietary spreadsheets that they've made to try to forecast how seasonal temperatures will impact the price of natural gas. So the idea there is if this winter is going to be super cold, people are going to need more and more natural gas to heat their houses, and that demand shock will cause the price to surge. And they can advise hedge funds how to trade these futures and stocks. And so there's a lot of money to be made with the knowledge of weather. And we'll talk about some more applications in the next few minutes. In a similar sense of hedging, we can look at insurance industries, and the general concept of hedging is not just to make money, it's to hedge against a potential loss. You're usually betting against your own interests when you're hedging, and this comes into play in the insurance industry. When there's a storm coming, so let's say there's a hurricane entering the Gulf of Mexico, and there's a real estate insurance company that insures properties along the Louisiana coastline. They don't want that hurricane to hit their properties because then they have to pay out insurance payments to people who live there to fix their houses. So what they'll do is they'll have an on-staff meteorologist try to like more accurately predict the exact landfall location of this storm. And then there's a trading platform, it's called Trade Weather, and there's other similar ones where they can go in and bet on where they think this hurricane is going to make landfall, so that if it does hit their properties and they have to make payouts, they're making money from winning this bet. So there are all these crazy applications of weather forecasting throughout industries to help companies avoid risks that are associated with weather. The example I usually go to is, let's say you're an avocado farmer in Mexico and you hear there may be a drought in the fall that's going to kill half your crop. You'll have fewer avocados to sell, but the price is going to go up. So what you'll do is you can buy avocado futures contracts so that when you have fewer avocados to sell, you have these avocado contracts that you bet on the price going up. So then it helps to hedge against your loss in your business. So weather plays a big role in a lot of businesses. Like I was just saying, agriculture. So I met someone who's employed as the meteorologist for Mars Candy Company, and he specifically does seasonal weather forecasting for coconut, cocoa, and peanuts to help Mars figure out how they should be pricing their candy bars in the coming quarter. So there are all these super cool applications that I find interesting. There's private consulting. So both Macy's and Applebee's pay private weather consulting firms. Macy's is trying to figure out what clothing line they should run next month. In November, should we be breaking out the winter coats? Should we have more like light wear gear? Applebee's is looking at what kind of specials menu should we run next month. In October, should we have like chili with like cheddar cheese and bacon, or should we still have like a watermelon salad? And moreover, now that we're in this scenario of restaurants only catering to outdoor dining, it's also about a safety perspective of having their outdoor dining rooms open. So what do we do more specifically? As I was saying, we're a hyper-local weather forecasting service in the southern Hudson Valley and Southwest Connecticut. We provide our subscribers and clients with near daily hyper-local weather forecasts and discussions. So we try to not only make the forecast more specific to your town, because when you go on the weather.com app, there's no like Meriden, Connecticut meteorologist for the Weather Channel. There are meteorologists that forecast for regions, and then artificial intelligence helps to fill it in. So we try to use our knowledge of the local geography and whatnot to make hyperlocal weather forecasts for our regions so we can be more accurate. But we also try to focus on the human impacts of our forecasts. So we talk about threats to schools and threats to safety and what it would be like to have a barbecue outside that day. And we also try to convey our uncertainty, because there's a lot of that. So every forecast that we send out, we put a score on it for how uncertain we are. We also provide text alerts and the ability for subscribers to reach out with questions and special forecasts. I think this is what really sets us apart, is our subscribers really like to reach out to us with quick questions like, I'm having a barbecue tonight, when's the thunderstorm coming? And that's more important for institutions, like when the Larchmont Library is deciding when they need to close during a snowstorm, we're on the phone with them to help figure it out. So this is who makes up our subscribers. 40% are just like weather enthusiasts, people who would rather read our updates than a magazine. And then we have like library administrators, school administrators, parents and teachers make up 35% of our subscribers because they want to know what's happening with their children's school the next day. These are what our updates look like that we send out during a snowstorm. So we try to focus on school risks, the exact timing, and we're breaking it down by region, intra-county. So breaking the counties down into smaller regions, because as many of you know, what's happening in Norwalk is not what's happening in New Fairfield. What's happening in White Plains is not what's happening in Mount Kisco during a snowstorm. Try to break the timing down as specifically as we can, and we have our confidence up here, and give like a more detailed personal discussion. But it's not all about the winter either. This is the report that we sent out for Tropical Storm Faye last week, and we work with summer camps that are trying to keep their campers safe during storms outside. And this is more of a specified report that a library would receive with an operations discussion. Why do people pay for our weather forecast when there's the National Weather Service and Weather Channel, and all these things are free? And this doesn't just apply to us. This applies to every application that I've been talking about so far of private weather forecasting. For us, we're looking at a local area, so we are hoping our forecasts can be more accurate. We're providing impact-based forecasts, and we try to put a personal touch on it, and people like to reach out. So I'm going to finish talking about us with this slide. These are two examples of different kinds of special forecast requests that we've gotten. This one on the left is someone in Norwalk who is planning the Christmas tree lighting and shot us a text, and we helped them to figure out when the snow would start, when it would be safe to hold this Christmas tree lighting. This one on the right is one of my favorites. We had a maintenance company that was doing a week-long maintenance project on a lighthouse in the middle of the Long Island Sound. And they needed to know, is it safe to have their crew out on the lighthouse all week based on wind and waves, but also the paint that they were using would only set in humidity below 65%. So we had to tell them each day, is it safe to be out on this lighthouse? And also, is it even worth working that day because will the paint set? So those are the kind of things we do. And if that sounds like something you're interested in, we made the special coupon code Larchmont, which can get you 20% off our service if you feel like you want to be a subscriber. That being said, being a forecaster is not the only thing you can do in the meteorology industry. We need a lot of researchers, and the professors that Jack and I have are all doing cutting edge research to try to improve our forecasting skills and our understanding of the atmosphere. Jack mentioned about how much our forecasts have improved in the past 20 years, and we're looking to get better, and there's still a lot of things we need to learn. For example, a lot of our hurricane track forecasts are based on like statistical extrapolations of previous storms that occurred in the same area and had similar characteristics. We're still learning a lot about what drives hurricanes tracks. We're learning a lot about like upper atmosphere dynamics in thunderstorms. There's still a lot to do in improving tornado warning time. So there's a lot of room in the industry for research. As I'm sure a lot of you know, when we send out a severe thunderstorm warning and then there's no thunderstorm, that we're still working to make it the best we can. And finally, this presentation was about weather and not climate, but climate and weather come hand in hand. Climate is about average conditions on more of a 30-year time scale. Politics comes in as we're facing climate change, and it's becoming increasingly important to have people who have an understanding of the atmosphere and how weather impacts our day-to-day lives, which is why, aside from studying meteorology in college, I picked up a minor in applied economics, because climate change is expected to cause trillions of dollars in damage throughout our lifetimes. So the industry is becoming increasingly important as we face these challenges. I'm happy to talk more about climate change, impact on weather during questions if people have any questions about it. With that said, we are happy to take questions now. Thank you so much for listening today.